Hi, my name is Nick, and I'm here to present the solution to problem B, Blackboard game. In this problem, we're playing a game on the positive integers from 1 to n. The way that this game works is we start by picking an even integer between 1 and n, and players will alternate turns. So player 1 starts by announcing some integer, and then the next player will announce an integer that hasn't been announced before, and you can only obtain a subsequent integer if you can take the most recently announced integer and either multiply it by a prime or divide it by a prime. And the person who loses is the person who cannot announce a number on their turn because all such numbers that they could obtain from this process have already been announced. So here in the sample case that was provided is n equals 5, and we can model it by this graph here on the left. And we can show that for this specific case, there is no winning strategy for player 1. So if player 1 announces 2, for example, then player 2 announces 1, and then player 1 announces, if player 1 announces 2, then player 2 announces 4, and then the game is already over. Similarly, if player 1 starts by announcing 4 as their first number, then player 2 is forced to choose 2. Player 1 is forced to choose 1, and then player 2 can announce either of their primes 3 or 5. So in this specific case, we can see that there is no winning strategy for the first player. In this problem, the bounds Rn goes up to 10 million, and the time limit itself is actually very strict, which will become relevant shortly. One thing that we can observe by looking at the structure of the numbers is if we count the number of primes that divide each number up to multiplicity, we can see that we can model sort of the integers as this bipartite graph. So one consequence of this is that we can derive this theoretical solution where we start by computing a maximum matching on the graph of all integers from 1 to n. And then we can consider removing some candidate integer k from the graph and then recomputing the maximum matching. In the event that the maximum matching decreases in size, then this is not a viable starting choice. In the event that the maximum matching retains the same cardinality, we can also show that with the matching, it's possible for the first player to win. So the nice thing about this strategy is it works for a pretty large range of values of n. Unfortunately, n goes up to 10 million, so the solution does not actually scale all the way to 10 million. So as a result, we have to sort of come up with a smarter solution that sort of cleanly handles larger values of n, where we cannot run this sort of matching solution. And there are a lot of different strategies that could work here. One strategy that we expect that some contestants will try is they will implement this matching solution, and then they will look at all of the valid values, the valid starting values for various values of n. They'll guess some pattern that probably works, and they'll just submit it without actually proving the strategy. For our purposes, we need to actually provide a deterministic strategy that does work. So here we have this sample graph that is presented on the right. So for sufficiently large n, we can show that there exist 3 unique primes, p, q, and r, where each of those is strictly greater than n over 4 and less than or equal to n over 3. And so If we consider this subgraph with these primes P, Q, and R, or 2P, 3P, 2Q, 3Q, 2R, 3R, and then 2 and 3, and then the player starts by announcing, say, 2P, then the game is sort of fairly deterministic. There are only 2 paths around this graph, and the ultimate conclusion is that the second player doesn't have a choice, and they will eventually get locked out. And so essentially this is how most of the winning strategies end up working. You use several of these large primes, and then you force the second player into staying within the subgraph. There are other possible constructions, but for our purposes, this is sufficient.